Have you ever just, stopped and thought about the rules that govern, well, pretty much everything? I mean, from a planet spinning around the sun to the car you're driving to work. There's this invisible rule book that's always in play. And that rule book? That's physics. Today, we're going to see how those big universal rules are also the ultimate rules of the road.
So let's start with something we all get, a road trip. Imagine a friend asks you to describe a drive you just took. What would you even tell them? It sounds like a super simple question, right? But what information do you actually need to give them the full picture of that trip? You'd probably hit on these four main questions. How far is it? How long is it going to take? How fast are we driving? And of course, which way are we going? And believe it or not, just by answering those basic questions, you've just outlined the absolute fundamentals of how we describe motion in physics. Now, to answer any of those questions properly, we need to be on the same page. We need a shared language. It's not enough to say, oh, it's pretty far, or we're going really fast. We need numbers, and those numbers have to mean the exact same thing to me, to you, to everyone. And that's where this idea of a universal language of measurement comes in. At its very core, physical measurement is just this. It's a process for turning the world around us into hard data that we can actually work with. It's how we give a precise, number-based answer to questions like how far or how long. This is, without a doubt, the very first step to solving our road trip puzzle. So, what does this universal language actually look like? Well, scientists all over the world agreed on a standard called the SI, or the International System of Units. What you're looking at here are the 7 fundamental SI units. Seriously, think of these as the entire alphabet of physics. It's kind of mind-blowing when you realize that every single physical thing in the whole universe can be described using some combination of just these 7 basic units. And just like you can combine the letters of the alphabet to form words, we can combine these fundamental units to create what we call derived units. This is what lets us describe more complex ideas, moving past just a simple length or a bit of time and into answering the real questions about our road trip. And this slide shows it perfectly. Just look at speed. To talk about the speed of our car, what do? We combine the fundamental unit for length, that's the meter, with the unit for time, the second, and boom, you get meters per second. We've just created a word in the language of physics that directly answers one of our big road trip questions. Okay, so we have our language, we have our units, but just knowing the language isn't enough, right? You have to use it correctly. And in physics, and really all of science, that means you have to understand the huge difference between accuracy and precision. And spoiler alert, they are absolutely not the same thing. Getting this distinction is crucial. Just like the slide says, accuracy is all about how close you are to the real, true value. If the speed limit is 60 miles per hour and your speedometer says 60, hey, that's accurate. Precision, though, that's all about consistency. If your speedometer always reads 55 every single time, it's really, really precise, but it's not accurate at all. You know, the classic bullseye analogy on this slide makes it crystal clear. Look at the top left. All the shots are clustered right in the center. That's the goal, accurate and precise. Now, top right, they're all clustered together, but way off the center. That's precise, but definitely not accurate. Bottom left, they're kind of all over the place, but their average is in the middle. So accurate on average, but not precise. And, well, bottom right is just a mess. Neither. In science and for our car speedometer, we are always aiming for that top left corner. All right, we've got our language of units, and we know we need to be accurate and precise. Now, finally, we can get back to our car and start describing its motion like a physicist would. We're about to dive into the world of kinematics. So kinematics, as you can see here, is all about the how of motion, not the why. It doesn't care about the forces, not the engine, not the friction from the road, not your foot pushing the pedal. Nope. It is purely focused on describing the motion itself. Where is something? How fast is it going? And how is that motion changing? Okay, now for a difference that is so important in physics, speed versus velocity. As you can see, speed just tells you how fast you're going. That's it. Physicists call this a scalar. It just has a size, a magnitude. But velocity tells you both how fast you're going and in what direction. We call this a vector. So saying 60 miles per hour is your speed, but saying 60 miles per hour north, that is your velocity. So what happens when that velocity changes? Well, that's acceleration. Now, most of us think acceleration is just speeding up, right? But in physics, it's any change in velocity. So yeah, hitting the gas is acceleration. But hitting the brakes is also acceleration. It's just in a negative direction. And here's the really cool part. Even turning the steering wheel at a constant speed is acceleration because you're changing your direction. And direction is a part of velocity. This slide really just lays it all out perfectly. You can see how these ideas build on each other, one after the other. It all starts with your position, where you are. A change in that position, that's your displacement. The rate you're being displaced, how fast your position is changing, that's your velocity. And finally, the rate at which your velocity is changing, that's your acceleration. See? It's this beautiful, logical staircase of ideas. Now, this is where it gets, for me, just absolutely amazing. These simple rules we just used to describe a car trip, they don't just apply to cars. They apply to an apple falling from a tree, a baseball thrown through the air, and even planets orbiting a star. This isn't just the rulebook for the road, it's the rulebook for the entire universe. So why should you care about any of this? Because this language of measurement and motion is the absolute foundation of our modern world. It's how engineers design bridges that don't fall down, how scientists launch rockets into orbit, how astronomers can study galaxies billions of light years away, and yeah, even how doctors figure out the exact life-saving dose of a medicine. It is literally everywhere. And if there's one single thing you take away from all this, let it be this. The physics that describes a car accelerating away from a stoplight is the exact same physics that describes an apple falling from a tree or Jupiter orbiting the sun. The scales are wildly different, but the fundamental rules of motion, they are universal. And in the end, that's the real power of everything we've talked about. By creating this shared system, this universal language, we get the accuracy and consistency you see in this quote. It means a biologist in a lab, an engineer on a construction site, and an astronomer peering through a telescope can all speak the same fundamental language. They can understand and build upon each other's work. And that leaves us with a really fascinating and kind of profound last question to chew on. If we truly know the rules of motion, if we can perfectly describe how something is moving right now and exactly how that motion is changing, what's really stopping us from predicting the future? Could we, in theory, calculate exactly where every single particle in the universe will be tomorrow, or a year from now, or a billion years